Electricity and magnetism. We've been talking about that for a while. With electricity, we know charges will produce electric fields. All charges produce electric fields. We know that positive charges, the field radiates outwards away from it. And negative charges, it points inwards towards the negative charge. We know that moving charges create magnetic fields, and the magnetic field makes circles around the moving charge. Turns out, it's not very common to not find an electric field without a corresponding magnetic field. They go hand in hand. And we know, for example, when we talk about induction, if we could change the magnetic flux, so even by changing the magnetic field, we can induce a voltage, which if you have a voltage, then you have an electric field. So by changing a magnetic field, we could induce an electric field. Turns out the opposite is true as well. If you change an electric field, it will create a magnetic field. But some of our main equations that we've talked about, for example, Gauss's law for electric fields, if we integrate the electric field over an enclosed area, that flux is equal to the charge enclosed by that area over epsilon naught. For magnetism, if we integrate the magnetic field over a closed area, we get 0. And that's because we have yet to isolate a magnetic north pole from its corresponding south pole. We know there's a potential difference if we integrate along an electric field line, but we can induce that potential difference as well by changing the magnetic flux with time, which that is Faraday's law, where we induce a voltage because of a changing magnetic flux. And that voltage is corresponding with an electric field. Our similar equation with magnetic field this is need to close. This equation was called Ampere's law. If you have current flowing through a wire, then you're going to have a magnetic field through the wire. Turns out, it was later discovered that this equation was not quite complete. This equation, this last equation for Ampere's law, correlates the current through a wire to the magnetic field it produces. So if I have a wire carrying current, then I know I have a magnetic field that circles the wire. But it turns out, if my wire is connected to a capacitor, and if that capacitor is in the process of charging or discharging, it creates a little magnetic field as well. And so this equation needs to be modified slightly to account for the charging or discharging of a capacitor. Because technically there's no actual current between those plates. Yet if I put a magnetic field detector in there, I would detect a magnetic field. The whole reason we get a magnetic field is because the electric flux in that region is changing. Now, electric flux is going to be the electric field times the area. Inside, between the plates of a capacitor, we know the electric field is eta over epsilon naught. It's a constant inside the plates of the capacitor. But eta is charge per area. Turns out those areas cancel. The epsilon naught is a constant, so I can actually pull that out of the derivative. The amount of magnetic field that is created is directly related to the rate at which that charge is changing. How fast the capacitor is charging or discharging. This dq dt here, if we bring the epsilon naught over, dq dt is equal to epsilon naught times the derivative of the electric flux with respect to time. This is called a displacement current. Now that's a little deceptive because it's not technically a current in that charges aren't physically jumping from one plate to the other, but they call it a displacement current just for the fact that it's a dq dt. It's a rate at which the charge is changing. So to make this equation complete, we need to add in this extra component there. So mu naught times the dq dt, our displacement current, which is epsilon naught dphi dt. That makes Ampere's law complete. It makes it so it is valid not only around wires, but around our charging capacitors. On a side note, this displacement current, we know for a capacitor, charge is equal to C times V, the capacitance times the voltage. We can also look at the displacement current. If we take the derivative of both sides, assuming the capacitance itself isn't changing for our capacitor, we end up with the displacement current equaling our capacitance times dV dt. So that works as well. So dV dt would be the rate at which the voltage is changing across our capacitor. So a capacitor, if it's in the process of charging or discharging, it will create a magnetic field. So a changing electric field will create a magnetic field. A changing magnetic field will create an electric field. That led scientists to start looking into the whole concept of relativity. It's all, whether you're seeing an electric field or magnetic field, is all a matter of reference frame. Say we were able to actually hold a charge. If I was holding a charge in my hand, we would see an electric field. Yet if I took the charge and started moving with it, to you guys it would be a moving charge, and you would see a magnetic field because of it. So, an interesting beginning to the concept of relativity. These equations, though, when it's there was a scientist, basically, James Clerk Maxwell, who took these four equations. The four equations were derived independently of him, but he took them individually and together realized that these equations describe electromagnetic waves. He took our equations here and wrote them in differential form, so in terms of derivatives rather than integrals, and discovered that the result he got looked just like the solution, the differential equation solution that describes a wave. So he was the one that realized that basically an oscillating charge will create what we call an electromagnetic wave. Now, electromagnetic waves, we mentioned before, electromagnetic waves have an electric field portion. Now, the equation I'm going to write right now is just a one-dimensional, so it's just a wave moving along a line. You can write it in terms of 3 dimensions if you just use an R rather than an X. So our electromagnetic waves have an electric field portion. It is oscillating sinusoidally. Whether it's an actual sine or cosine graph, though, just depends upon when you start looking at it. But an electromagnetic wave also has a magnetic field portion. So Emax represents the maximum value of the electric field. Bmax represents the maximum value of the magnetic field. As a reminder, remember K is the wave number, which is equal to 2 pi over lambda, lambda being wavelength. So lambda is the distance from peak to peak. Omega is the angular frequency, which is related to regular frequency in hertz by just the unit conversion of 2 pi. Just like waves before, when we talked at the beginning of the semester, the speed of the wave is equal to wavelength times frequency, which is the same thing as omega over k. Electromagnetic waves travel at the speed of light, unless they're in another medium. If they enter water, for example, they do slow down. And they slow down according to the index of refraction, like we talked about at the beginning of the semester. All electromagnetic waves travel at the same speed in a vacuum. That's something unique about electromagnetic waves, is that they do not need a medium to travel. They can travel through a vacuum, which is most waves we know of require a medium. We have another relationship that falls out from this equation. Turns out, if you were to take these equations and plug them back through the differential equations, we find out a couple of things. We find out that C is equal to 1 over the square root of mu naught times epsilon naught. That's where the speed of light came from, in terms of knowing the exact value. But we also find that C, the speed of light, is equal to the maximum value of the electric field over the maximum value of the magnetic field. That means the electric field is always 3 times 10 to the 8th meters per second bigger than the magnetic field. So the electric field is always a lot bigger than the magnetic field. Now, in terms of their orientation, if this is the electric field versus time, the magnetic field, notice they're both sine of kx minus omega t terms. That means these two are in phase. That means if one is 0, the other is 0. If one is at a maximum value, the other is at its maximum value. They don't have the same maximum value, but they'll both be maximums at the same time. But it turns out the electric field and the magnetic field are always perpendicular to each other. So as our electric field oscillates up and down, our magnetic field will oscillate out of the board, then into the board, and out of the board, and into the board. I do not draw three-dimensionally very well, so I'm not even going to try. There's a good picture in your book if you want to see it. So the two are always perpendicular to each other, but they're in phase. So they're 0 at the same time, and their maximum values are at the same time. It turns out, if you look at the direction of the electric field crossed with the magnetic field, that gives you the direction the wave's traveling in, the direction of the velocity. So if E is upward and B is outwards, my electromagnetic wave is traveling to the right. Now, the value of E cross B does not equal V. It's just the directions that correlate. So we're going to talk about just a couple of different properties of electromagnetic waves. But one thing we're going to need to talk about is an average. So on average, what is happening with our electromagnetic waves? When we talk about the intensity, for example, intensity of a light or intensity of a laser, we're talking about the average intensity. If the electric field and magnetic field are changing, which they are, if they're oscillating, then the actual value of the intensity is oscillating as well. On average, the electric field is 0. The average of a sine function is 0. But that's a little counterintuitive. Even though the true average is 0, electric fields have an intensity. I can take a laser and I can shine it on something. If I have a light bulb, I can turn on the light bulb and see light. What we do to talk about, it's not going to be a true average, but the way we talk about the averages is what we do is we look at first squaring our electric field. What's that going to do to this graph if I square it? Right, it's going to make everything positive.
And weight the bigger value is bigger.
Yes, that's what we're getting to. So now our function is Emax squared times the sine squared of our kx minus omega t. So now that we've squared it, now we're going to take the mean value. The mean value depends upon the mean value of the sine squared function. Sine squared function, the mean value is 1/2. Now we're going to take the square root of it. When we take the square root of the mean value of the electric field squared, what we get is called an RMS value. RMS stands for root mean square. We squared it, we found the mean, we took the square root of it. That's what RMS stands for. So this is the value we have, it's called an RMS value. The RMS is what we use to talk about our electric field on average. Now it's not a true average in that it's not the actual average of the sine function, but it works in allowing us to talk about on average what our electromagnetic wave is doing. By the way, if we did the same thing with the magnetic field, we'll get a similar relationship. Anytime we talk about RMS values, it's always going to be a max value over the square root of 2.
When it's sinusoid.
Yes. Yes.
It's a triangle and it's like root 3.
Yeah, so a sinusoidal function. Which, by the way, this relationship where the speed of light is equal to Emax over Bmax, Emax would be the square root of 2 times ERMS. Bmax would be the square root of 2 times BRMS. If I plug those in for Emax and Bmax, the square roots of 2 will cancel. This relationship works as well using our RMS values. So if you know an RMS or maximum value of one of them, you can easily find the corresponding value for the other.
Can you interchange those Emax? Like you have one RMS and one like Bmax and BRMS. Do they still work?
So use an ERMS and a BRMS? Or an ERMS and a Bmax?
Yeah.
No.
Okay.
They either both have to be max or they both have to be RMS.
But you can change one to the other.
But yes, you can easily convert from one to the other using these relationships.
Okay.
Okay? So if you have an RMS value for one, you can use this relationship to find the RMS value for the other, and then come back here and find the max. But yeah, if they either both need to be max values or both be RMS values. You can't have one be RMS and one max. Unless you've used these equations to write it that way. Okay. Other questions?